Okay, so we're going to continue with our next video here, and it's the quantum theory of the atom. Okay, and we all know we've got what we call the Bohr atomic model, and Bohr proposed that the hydrogen atom has only certain allowable energy states, and suggested that the single electron in a hydrogen atom moves around the nucleus in only certain circular orbits. Okay, de Broglie stated that electrons had wave-like characteristics. So we talked about waves from the previous video, and he stated that he believed these electrons had wave-like characteristics, and so he came up with the following equation: that wavelength, there's your wavelength symbol. You have m for mass of a particle, v for velocity, and h, again, Planck's constant. Okay, so to figure out all the things that he wanted to figure out, he's got wavelength equals Planck's constant divided by the mass times the velocity. Sorry, not volume, velocity. And this was how he came up with his wave-like characteristics for electrons. So we have the Heisenberg uncertainty principle, and he basically concluded that it is impossible to make any measurement on an object without disturbing the object, at least to a certain extent, a little bit disturbing it. And so his uncertainty principle states that it is fundamentally impossible to know how precise both the velocity and the position of a particle are at the same time. Now, there's another guy, Schrodinger. He had a wave equation as well, and he combined the ideas of both Bohr and de Broglie. And the atomic model in which electrons are treated as waves and particles is called the wave mechanical model of the atom, or more commonly, quantum mechanic model of the atom, which that's what we're talking about, the quantum models of atoms. So now you have this new working model, the quantum mechanical model of the atom, and you have these energy levels, okay? And you basically start with the major energy levels of an atom, and each level is a certain distance from the nucleus. So each energy level gradually works its way out. The higher levels contain more electrons than the lower levels. And so you have these energy sublevels as well, and they are sections within the principal energy levels. And they're represented by letters S, P, D, and F. Okay, and the principal energy level number indicates how many orbitals are in that level. So you have S equals 1, P equals 3, D equals 5, and F equals 7. And each of these orbitals has different orientations. And each orientation holds two electrons that spin in opposite directions. Remember, those electrons like to oppose one another. And so here are the orbitals on the table, and where those S, P, D, and F orbitals, what elements fill what orbitals on the periodic table. Okay, and then we start working into electron configurations and orbital notations. So both are just the arrangement of electrons in an atom. Orbital notations use arrows to represent electrons, and electron configurations look like this. Okay, so, and I'll show you an example of orbital notations in just a moment. But in an electron configuration, you'll have 1s2, 2s2, 2p6, 3s3, 3p6. That's just an example of one. And there are several rules to writing each one of these, and they are slightly different. Okay? The Aufbau principle. Okay? This would be like on the periodic table, you would have increasing energy, so you have this principle of as you go from 1s to 2s to 2p and so on, you have an increasing energy level as you work from the top to the bottom and from the right to the left. the chart. Each electron must occupy the lowest energy level first. So we always want to fill up the lowest one first. Okay, so those are the lowest ones, and we're working to the highest ones. Okay, the Pauli exclusion principle are that two electrons that share an orbital must have opposite spins. Okay, we talked about that in just a second ago. So in chemistry, we designate the spins with arrows. Therefore, if you got two electrons enter an orbital, they must enter in opposing arrows. This is the reason why you see an up arrow and a down arrow, to demonstrate that these electrons are spinning in opposite directions in that orbital. Then you have Hund's rule. You must have one electron in each orbital with the same spin before the electrons will pair up. Okay, so you must fill each orbital before you pair. For example, if you have 3 orbitals, and again, don't forget that each orbital can hold at most 2 electrons. You want to add 3 electrons. So how would they enter? What do you think? Do you think it will enter with no arrows? Do you think they will enter with 2 opposing, or 1 opposing the other, and then the next arrow, or do you think it'll be 3 ups? And the answer is the one with 3 up arrows. Remember the rules, right? I'm going to go back and show you. You must fill each orbital before you pair. So you've got to fill, if we go back and look at this, you have to fill each one of those orbitals before you get to pair. Remember, we only had 3 electrons, but we can't pair any of those first. We've got to fill each orbital. So, orbital notation. Before you start writing arrow diagrams, there's a few things you need to know. S can only hold a max of 2 electrons, an up arrow and a down arrow. P can hold a max of 6 electrons. D can hold a max of 10 electrons. And F can hold a max of 14. So in orbital notation, also, S has 1 orbital, P has 3 orbitals, D has 5 orbitals, and F has 7 orbitals. And remember that for each orbital, they have to have an electron spinning in opposite directions. Okay? So what do you notice about the number of orbitals compared to the number of electrons? Well, it's half, right? Because remember, S can hold 2, P can hold 6, D can hold 10, and F can have 7. Well, that's because we got to have those 2 electrons spinning in opposite directions for each orbital. Well, if you looked at the F orbital, for example, F can hold 14 electrons. It has 7 orbitals. We got to have 2 electrons in each orbital. 7 times 2 is 14, right? Okay, so lastly, you need to know the sequence of orbitals by Aufbau's diagram. So you're going to just follow the arrows. 1s fills first. Then notice that 4s will fill before 3d. Okay? So if I'm looking at this, I am going to fill 1s, then 2s, then 2p, then 3s, okay, then 3p, 4s, 3d, 4p, 5s. So do you see how this works? See, we start with 1s and we work from right. We work in the direction in the arrows. So we start at the end of the ray that's there, and we work to the tip of the arrow, which is why we would go 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, and so on. Okay, here's some examples. And you can look at the following web lesson. You can just click that or type it in. Okay, and orbital notation. Okay, you're going to write the arrow diagram for sodium. Arrows represent electrons, so before you start, you remember you need to find the number of electrons that sodium has. Okay, remember sodium, how many does it have? It has 11, right? Atomic number is 11. That tells us the protons and electrons. So you keep going till you reach 11. And where do you always start? With 1s. So there we go. There's 1s. Where to next? 2s. Okay, remember we got to fill them up before we pair. So there's where we are so far. 1s, 2s. And how many electrons have you used so far, right? We've used 4 because we filled 1s and 2s. So what's next? 2p. Well, remember, p can hold 6, right? And there we go. So we get 1s, 2s, 2p, and now we're going to that last electron, and it goes in 3s, right? So this would be the orbital notation for sodium. 1s, 2s, 2p, 3s, with the arrows in the corresponding order. So let's draw the arrow diagram for bromine. Sorry, I gave you a little hint there. Okay, so we know there's where we start, right? And that's where we end, because bromine has an atomic number of what? Anybody remember? Well, let's see. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 35, right? And I just counted up as I went, but yes, bromine's atomic number is 35 on the periodic table, so that means it has 35 protons and electrons. And if you go back and look at Aufbau's diagram, you can simply follow the arrows and determine that I've got to go to all the way to 4p. In the third orbital of 4p is where I would stop with my 35th electron. It's really very, very simple once you start doing this, if you just follow the rule. Okay, so now we're going to take a moment and draw the arrow diagram for sulfur. Whoops, sorry. And gave you a little clue there that it is going to get to 3p. And this is just some practice, so I'll let you do this on your own. And as we move to electron configurations, okay, writing electron configurations is just a shorter way for writing the arrow diagram. Now we're not drawing the arrows, we're simply writing in what you have. And you'll start with 1s and continue the configuration just like you did for the rest, till you get to the correct number of electrons. And the number of electrons in each orbital, are written as superscripts. So I'll show you. Remember, S equals 2, P equals 6, D equals 10, and F equals 14, just like it did with the arrow diagrams of orbital notation. So you just follow the chart again. So we're going to write the full electron configuration for K. So K is 19, right? Atomic number 19, it has 19 electrons. So this is how we would write K. Now if we were drawing arrows everywhere there's a superscript, that's how many arrows we would have. Obviously, if it's an even number, we would have one up and one down arrow for that even number. So like we would have an up and a down arrow for 1s. We would have an up and a down arrow for 2s. We would have 3 ups and 3 downs paired up for 2p6. So you get the idea. We're just writing superscripts, or what you might call exponents for those letters, to tell us how many arrows we had. So let's write the full electron configuration for krypton. Krypton's 36, right? So 36 electrons. We're going to fill, if you remember for bromine, we're going to have one more electron. So it'll fill all the way up 4p to 6. And so here's what it would look like. Again, remember that the exponent or the superscript just tells us how many electrons we have in each level, and we know that if we fill up all the orbitals, then we'll get the full number for that letter. Okay, now for phosphorus, it's 15. So here's the electron configuration for phosphorus. Okay? And reading the periodic table, the S block, the first two columns of the periodic table, starts with one S. The P block, groups 3 through 8A, 3A through 8A, 6 columns. They start with 2P. The D block, the center portion of the periodic table consisting of 10 columns, starts with 3D, and the F block, the two bottom rows of the periodic table consisting of 14 columns, starts with 4F. So, and again, there's that same diagram, right? The S block, the D block, the P block, the F block. Noble gas configuration is just a shorthand way to write an electron configuration. Okay, so there are some steps for that as well, and they are: first, you're going to find the element. 2, find the noble gas before that element. So group 8A, that's where the noble gases are, and you're going to place it in brackets. So then you're going to move one spot. So you're going to start the configuration from there and keep going until you get to your element. So for example, you're going to write the noble gas configuration for sodium. Well, the first noble gas before sodium we got to find, which is neon. Okay? So we're going to put that in brackets, right? And then we're going to move one spot and start the configuration from there. So neon 3s1, because neon is obviously 10, right? And then neon has 10 electrons, so we can put it in brackets, and we know that the next one after neon is 3s1. So we just write 3s1, and there's our noble gas configuration. Okay, let's try it for bromine. Argon's the first noble gas before bromine, so we put it in brackets. Okay, and then we go all the way to finish it out. So we have what? Let's see, 12, 17. So we know argon's 18, because that would be 35. So we put argon in brackets. That represents, when we do that, 18 electrons, and then we just write the remaining 17. Okay, you only go one noble gas before your element. So if we were to write the noble gas configuration for manganese, okay, so we find the noble gas before it. Again, it's argon. Argon's 18. Manganese has an atomic number of 25. So all we must do is write the remaining 7 and put them in the correct orbitals. Okay, final entry configuration. That's the last thing in an electron configuration. It's like a roadmap to our element, okay? And it can identify the element. So what is the final entry configuration for silicon? So you're going to find silicon, and what block are you in? S, P, D, or F? Well, you're in 3P, right? So how many spots are you into P? 2. So the final entry configuration is 3P2. Very simple, right? You're just writing where you are in the final spot. So the final entry configuration for Ag is simply 4D9. What is the last spot that you hold, and how many electrons occupy those orbitals? That's all you're doing. What is the final entry configuration for chlorine? Okay, so very simply, what's the last spot? It's 3p6. Okay, and the final entry configuration for sodium. Again, this is just practice. I know I'm going fast. Feel free to stop the video and practice it, write it out, and just go through it yourself, and then you'll find that sodium 3s1 is the final entry configuration that you have. Okay, what element has the final entry configuration of 4p3? So now we can always identify this. We can find out what elements holds the spot 4p3, and we just look, and we know that is As, right? 4d1 is Y. Whoops, sorry. And so you can see that with final entry, we can still determine what the element is, or we can use final entry to write, we can determine what the element is from our final entry, or we can do it in reverse. We can write final entry to represent our element. Okay. I know there's a lot of information in this video about doing notations. You're going to get plenty of practice during the weeks that we do this, and so don't feel intimidated. It's not as hard as it looks. I know I went fast and went through this video quickly, but I really think that we'll all be able to understand this once we get some practice and some more explanation in class.